The paper of the day is Chain Replication for Supporting High Throughput and Availability. Chain replication is a new approach to coordinating clusters of fail-stop storage servers. The approach is intended for supporting large-scale storage services that exhibit high throughput and availability without sacrificing strong consistency guarantees. Besides outlining the chain replication protocols themselves, simulation experiments explore the performance characteristics of a prototype implementation. The paper also discusses throughput, availability, and several object placement strategies, including scheme based on distributed hash table, routing, etc. To better understand the throughput and availability of chain replication, paper performed a series of experiments in a simulated network. These involve prototype implementations of chain replication as well as some of the alternatives. Because we are mostly interested in delays intrinsic to the processing and communication that chain replication entails, they simulated a network with infinite bandwidth but with latencies of 1 milliseconds per message. First, they considered the simple case where there is only one chain, no failures, and replication factor is, that is T, is 2, 3, or 10. They compared throughput for 4 different replication management alternatives. One is chain, that is the chain replication, primary backup strategy, weak chain. The chain replication modified so query requests go to any random server, and then there's a weak primary backup strategy. The primary backup strategy was modified so query requests can go to any random server. In the second series of experiments, the paper did multiple chains and no failures. If each object is managed by a separate chain and objects are large, then adding a new replica could involve considerable delay because of the time required for transferring an object state to that new replica. If, on the other hand, objects are small, then a large storage service will involve many objects. Each processor in the system is now likely to host servers from multiple chains. The cost of multiplexing the processor and communication channels may become prohibitive. Moreover, the failure of a single processor now affects multiple chains. A set of objects can always be grouped into a single volume itself, something that can be considered an object for purposes of chain replication. So a designer has considerable latitude in deciding object size. For the next set of experiments, they assume a constant number of volumes. A hash function maps each object to a volume and hence has a unique chain. And each chain comprises servers hosted by processors selected from among those implementing the storage service. In the another set of experiments, they tested the effects of failures on throughput. With chain replication, each server causes a 3-stage process to start. Sometimes they conservatively assume 10 seconds in their experiments elapses before the master detects the server failure. The offending server is then deleted from the chain. The master ultimately adds a new server to the chain and initiates a data recovery process, which takes time proportional to how much data was being stored on the faulty server and the available network bandwidth. The other series of experiment was around large-scale replication of critical data. As the number of servers increases, so should the aggregate rate of server failures. If too many servers fail, then a volume might become unavailable. The probability of this depends on how volumes are placed on servers and in particular the extent to which parallelism is possible during data recovery. They investigated 3 volume placement strategies. First is a ring. Replicas of a volume are placed at a consecutive servers on a ring determined by a consistent hash of the volume identifier. This is the strategy used in CFS and PAST. The number of parallel data recoveries possible is limited by the chain length, T. Then random R&D par. Replicas of a volume are placed randomly on servers. This is essentially the strategy used in GFS. Notice that given enough servers, there is no limit on the number of parallel data recoveries possible, and then there's a random sequence. The random par was for random parallel. Then there's a random sequence. Replicas of a volume are placed randomly on servers as in random parallel, but the maximum number of parallel data recoveries is limited by T, as in the ring. The strategy is not used in any system known to the authors, but is useful benchmark for quantifying the impacts of a placement and parallel recovery. Looking at the contributions, the main contribution of this paper is the chain replication concept. The chain replication supports high throughput for query and update request, high availability of data objects, and strong consistency guarantees. This is possible in part because storage services built using chain replication can and do exhibit transient outages, but clients cannot distinguish such outages from lost messages. Thus, the transient outages that chain replication introduces do not expose clients to new failure modes. Chain replication represents an interesting balance between what failure it hides from clients and what failures it doesn't. When chain replication is employed, high availability of data objects comes from carefully selecting a strategy for placement of volume replicas on servers. Paper experiments demonstrated that DHT-based placement strategies availability is unlikely to scale with increasing the number of servers, but they also demonstrated that random placement of volumes does permit availability to scale with the number of servers if this placement strategy is used in concert with the parallel data recovery as introduced for GFS. Let's talk PS score for this paper. Overall, this paper is a decent read, so it gets 9 out of 10 on readability. With 14 pages long, it scores 8 out of 10 on length. It's a research prototype with pretty good description, so that makes it 9 out of 10. Its industry value and learning meter is very high, with adoption in many production systems, so it gets 9 out of 10 on each, with overall PS score of 9 out of 10.